Hello everybody, welcome to this episode of Programming and Algorithms. In this episode we're going to look at software testing. So let me recall when I was young and I learned to program. When I learned to program first, the best thing ever that would happen would be if I could get the program to compile without any errors. So for a long time when I was learning to program, I'd write a program, compile it, and then it'd say, this program has 792 errors. Then I'd make some corrections, and then I'd go down to, this program has 4 errors. Then I'd make another correction, and I'd say, this program has 1,900 errors. Then I'd make some other correction, and I'd say, this program has no errors. Then once it compiled, I thought, okay, great. I don't care if it even works or not. I'm happy enough now that it's compiling, so that's a miracle. Unfortunately, I suppose, particularly if we're thinking about working in a professional environment, not only do they want code that compiles, but they want code that works as well. Not only do they care that it works, but they want it to work well. So we have software testing, which helps us think about how to make code work. So I would think it's very much like why flights do pre-flight checks, when in general the chances are the plane is working fine. Why do pilots do pre-flight checks? Because, you know, it's a serious business and it's always as well to check things, and it's the same with programming. Even if you're fairly confident your code is working fine, it's always well to check things and test things to make sure there aren't any errors in it. That makes software testing a really interesting kind of task, and I think a lot of people, when they think about software engineering, the building of software, they only think of the programming part of it. The same way when people think about doing science experiments, they think about the chemicals and the retorts and the beakers and all that, and the chemicals flowing through the tubes. As we know with chemistry experiments, in general, the chemistry experiment is designed and carefully worked out long before any tubes are hooked up, and equally once the chemical is produced, it's tested any number of times to make sure it's the right thing. And in the same way with developing software, the programming bit is the bit I think that they show a lot in movies and TV, but the design of the software before the programming and the testing afterwards are really crucial components. And a career as a software tester is an incredibly challenging and very interesting job. I think it really is like Sherlock Holmes. You're trying to analyze the software and try and find problems with it or issues with it, or try to understand how the developer has written the code and look at different ways it could be done. Because in general, how IT projects work, anyway, in my experience, when I was an IT developer, typically one of our customers would contact us and say, we need a sales order processing system. So I'd sit down with them and say, all right, well, what does the sales order processing system need to do? It needs to do goods notes, dispatch, invoice, orders, things like that, foreign exchange, blah, blah, blah. So we'd define and design the system, then we'd develop it, and then whoever had developed the system or whatever group developed the system, the software would be passed off to a different group of computer people who would test the software to make sure it does everything, to make sure it checks for unusual circumstances, and it handles all the issues as required. And then finally, once the testing is done, it's handed over to the customers. Regrettably, I think people's levels of expectation of software is very low, so it seems perfectly all right for large companies to release big software systems with loads of bugs in it. I won't name any particular large computer company, and I won't name any operating system they've ever released, but I will say that there have been a number of large software companies who have released a number of operating systems that have had thousands of bugs in them. And we always make the analogy with a car. If you released a car, if Toyota released a car that had 1,000 little problems with it, like the rear view mirror doesn't work or the roof keeps falling off, people would not buy that car, whereas people have a lower level of expectation with software, and they kind of accept an odd old blue screen every once in a while, which is a shame, because if they didn't, software would be tested properly, and if software was tested properly, then it would work properly. But companies are too much in a rush to just get the software out and not pay for proper testing. Testing is a really vital component, and I think if we can develop the good habit of doing it now in our first year of learning to program, more the better, more power to us. Historically speaking, I suppose testing probably goes back to the 1940s, and in 1944, during the Second World War, in America, in Harvard University, Howard Aiken developed a computer, and he was a pretty smart guy, and with the help of Grace Hopper, he developed this Aiken machine. Grace Hopper wrote the first compiler in the first computer programming language, A0. One day she was looking at the Harvard machine and found that there was a moth trapped between two relay points in the system. So she wrote, a bug has been found in the system and we have debugged the machine. So she took the bug out of it, and indeed this is a picture of the logbook, and she typed the moth onto the logbook. So this moth was causing an electrical short that was causing the program not to work. So when we use the term bug, what we mean is any error in the code that is causing problems, but the term derives from an actual bug that was found in an actual computer system that was causing a short to occur. We have other terms for bug. They're sometimes called defects or faults or problems or errors or incidents or anomalies or variances or failures, inconsistencies, product anomalies or product incidents. Anytime the system doesn't do what it's supposed to be doing, either a small little problem or a big problem, it's a bug. The code isn't written correctly. So we need to test for those during the testing phase that generally follows the development phase. There's an interesting paper that discusses the different eras of testing, and what they say is between 1945 and 1956, testing and debugging was almost the same thing. The goal of checking the software was to check, is there any mistakes in it? And that's the extent to how far testing went. Whereas as time went on, modern testing not only checks does it have errors, but more like what quality of service does it give to the user. If the software works with 10 users, let's try it with 100 users or 1,000 users. So if we stress test the system, or if it works with 100 variables, let's try it with 20,000 variables and see, does excess of data or excess of users, does that impact whether the system works or not? Clearly between 1945 and now, the number of lines of code and the sophistication of software has increased significantly as well. So therefore we have to test in different kinds of way. So let's say now there's a big concentration on user interface testing. So what the user is presented with, does that code work well, is considered very important. But also you have to think, does the background logic of the system work well? So if I'm writing a program to calculate compound interest, does it calculate compound interest correctly to the correct number of decimal places and all that sort of thing? So in terms of methods of software testing, I like to think of it using the box approach. So the 3 box approaches to software testing. We have black box testing, we have white box testing, and so-called grey box testing. So black box testing is if the developer develops the code, compiles it, has it running, and then gives it to a software testing team and says, don't look at the code at all, just run it and see if it runs, does it work? So let's say the system is to input your name and address, your age, your job title and things like that. Check if I put in the name Damien Gordon, does it work and does it record Damien Gordon? And if I ask what did it record it correctly? Put in blank blank and see what happens then. Put in Damien blank, put in blank Damien, put in instead for a name 123728941 and see, does the system recognize, well, that's a number, not a name. So treat the system as a black box, as if we don't know what's going on inside the system, and just check the user interface elements and do they work correctly or not. The opposite of black box testing is white box testing, where the testers actually go through the code itself, go through the logic, go through every if statement, go through every while loop, check will the conditions always be satisfied, check will it always go into the if, the else, check if we've a case statement that we catch all the other bits. So to check if the whole system works from the inside out. So that's the exact opposite. Black boxes, not looking at the code at all and just looking at the user interface. white boxes looking at the code and checking the logic, and then grey boxes somewhere in between, where we know the main structure of the system, and we can test a little bit of the internals, but also test a lot of the externals as well. And that might even be looking at how the system works from the user interface, and then saying how you would design the code for that, and then looking at the actual code and comparing how you've designed it, how the developers have designed it. In terms of types of testing, if we have a 10,000 lines of code and we just test one if statement at a time, or one while loop at a time, we just pick that out of the code and test that, and we put it in what's called a test harness, or a program that will run that. We call that unit testing. So we're just testing one unit or one little bit of the code at a time. If we look at each module, and we talked about modularization before, so if we look at what values are going into the module and what values are being returned back out of it, and we treat each module, again, take it out of the code and stick it in a harness of some kind to test it, we call that module level testing. If we look at how modules talk to each other and what values they pass between each other, we call that subsystem testing. And if we look at how all the subsystems and modules work together, and how successfully they communicate, we call that integration testing. And it's that integration testing really that we're looking at how well the system works, what impact it has on performance. Is it eating up memory? Is it eating up processing power? Or is it being done as efficiently as possible? If we stick 500,000 users on it, does it go much slower than if we stick 50 users on it? And if we do loads and loads of transactions from one user in a loop, what impact does that have? So that could be volume testing. So that integration testing, we're putting it all together. And then finally, acceptance testing is, let's get the customer to give us a copy of their database or their data, and let's pump real live data into the system and check that it's giving the answers the customers want. And that's acceptance testing. So there's levels of testing from each line of code up to the whole working system. In terms of software testing tools, there's a range of tools we can use that allow us to explore the different, not only whether the system works and debug and trace and step through the code, but also to analyze the performance of the software as well. There's a lot of tools that I like a lot where you can record you doing an activity, and then once you've got that record of you doing it, play it over and over again under different scenarios, which is great. So there's a range of tools there, and we'll do that in a lot more detail in the next semester. Thanks very much for this. We'll see you on the next episode.